The Soil Conservation Service assists farmers in planning a conservation irrigation system that is adapted to soils, the topography of the land, and the crops raised. A well-designed and developed system will efficiently use the water resources, minimize erosion, and determine if irrigation is needed or desirable in the total resource management system. This 5-part series is to introduce you to information necessary to help you assist farmers in planning a conservation irrigation system. Your local soil survey report and your state irrigation guide are needed to help farmers plan their irrigation system. Upon completion of this part of the module, you'll be able to, 1, list the 4 factors which have a bearing on crop production as it relates to irrigation. 2, name the 4 sources of water for irrigation. One of the most significant risk factors in agriculture is the weather. Seldom is rainfall adequate to obtain optimum crop production. Consequently, more land is being irrigated than ever before. Before a farmer invests in an irrigation system, there are several factors to be considered, one of which is determining whether or not to irrigate. The farmer must answer such questions as, how much effect will irrigation have on increasing yields and improving the quality of the crops? How much water will be needed throughout the crop's growing season? Will a satisfactory and adequate source of good quality water be available to meet these needs? First, let's consider the effect of irrigation on crop production. 4 factors are considered, all of which have a bearing on crop production as they relate to irrigation. They are the amount and timeliness of rainfall, the effect of supplemental water, the effect of land drainage, and the fringe benefits. The first factor is the amount and timeliness of rainfall. The availability of rainfall for growing crops varies greatly from one section of the country to another. These variations of annual precipitation in the United States may be seen in this map. Note that arid states in the western part of the country receive from 0 to 10 inches of rainfall annually. States in the more humid eastern part receive from 40 to 60 inches. In the arid and semi-arid areas, crops may not be grown at all without irrigation. The monthly distribution of rainfall is an important factor. The yearly rainfall may be more than adequate to produce a crop, but the monthly rainfall may be much less than is necessary to meet the crop needs during the peak growing season. The second factor to consider are the benefits expected by adding supplemental water or irrigating. One important benefit that should not be overlooked is improved crop quality. Larger and more uniform fruits and nuts, better color in fruits and vegetables, and increased yields and better quality of field crops. Supplying additional water to a crop during its growth cycle results in increased yields. For example, a better stand is possible if moisture is available to germinate the seed after planting. More plants can be grown per acre by using closer row spacings. Plants make more efficient use of fertilizer because plant nutrients must be in soluble form to be taken up by plant roots. And the ample water allows the use of improved varieties such as corn hybrids developed especially for irrigated culture. A third factor to consider is drainage. Good drainage and irrigation go hand in hand in a complete water management program. Plants cannot grow normally in waterlogged soils because plant roots do not develop properly. This reduces the plant's capacity to take up nutrients. 2 types of drainage systems are used to remove excess water from a field: surface drainage and subsurface drainage. Surface drainage is accomplished by land grading, land planning, or constructing shallow open ditches and waterways. A subsurface draining system is a network of ditches or buried drain pipe, usually corrugated plastic tubing. It is installed at a sufficient depth to intercept and carry off excess subsurface water. Both surface and subsurface drainage systems may be needed. The fourth consideration are the fringe benefits that irrigation can provide. These are often as valuable as supplying water to the crop. Irrigation may be used in two ways to prevent or reduce crop losses from spring frost or freezing weather. One, a technique called bloom delay, has been developed for tree crops. This procedure, which is used to retard tree bud growth, reduces the probability of blooming during a spring freeze. And two, for frost control of freeze protection, heat can be added to plants by applying water through sprinklers to a fruit or vegetable crop and then allowing the water to freeze on their surfaces, releasing the heat of fusion. Similarly, evaporative cooling is used to lower the temperature surrounding plants during excessively hot days. Another fringe benefit is the application of chemicals to crops through an irrigation system. Fertilizers, herbicides, and pesticides may be injected directly into the irrigation water. This is done by use of a high-pressure pump and a tank that holds the chemical solution. Also, animal wastes in liquid form can be applied or distributed through an irrigation system. An adequate water supply is essential to any irrigation system. In planning an irrigation system, the district conservationist must make a comparison of the amount of water available to the total amount of water the crop will require during the growing season. Now that we know the effect water has on crop yield, let's consider the amount of water necessary. The first consideration is to determine the total amount of water needed by the crop during a season. This is called seasonal consumptive use, or the seasonal water demand. It varies somewhat according to geographical location. To determine total water needs for a given crop in your location, multiply the total water use per season by the total number of acres of the crop you plan to irrigate. Another consideration is the peak use rate of water demand for a crop. A growing plant uses much less water during early stages of growth than it does as it approaches maturity. Water use for most crops is greatest during the fruiting or reproductive stages of growth. The rate of water use during this period is called peak use rate. These rates vary for different locations because of climate and soil conditions. Remember that the water source for the irrigation system must supply the water needed to meet the peak use rate of the crop without rainfall during the irrigation cycle. For the crop water requirements and use rate in your area, refer to your state irrigation guide. When you have established how much water is needed to meet the crop's seasonal and peak use requirements, the next step is to determine whether there is or can be provided an adequate source of water to meet these requirements. You need to consider the sources of water available to the farmer, water rights laws as they affect the use of that water for irrigation, the distance the water will have to be pumped to reach the crop you want to irrigate, and to what height the water must be lifted or pumped to reach the field to be irrigated. The sources of water for irrigation are streams, lakes, ponds or reservoirs, community pipelines or canals, and wells. Sometimes a combination of these sources may be used to provide the needed water. Streams are a common source of water for irrigation, but you need to check on the stream's dependability. Find out from history what kind of flow the stream will have when it will be used for irrigating, which normally is the lowest flow rate of the stream. Lakes, ponds, and reservoirs may be used as water sources, providing they are of adequate size to supply the water needs throughout the growing season. The amount of water feeding the lake, pond, or reservoir to replace what is being taken out has a great deal to do with what size the body of water needs to be. A field supply line may be either an open canal or a pipeline. In either case, it is the means by which water is delivered from the source to the field. Wells are used as a source of water for irrigation in many parts of the country. In some parts, however, water availability from wells is quite limited or non-existent. The map indicates areas where groundwater supplies are located in the United States. The blue-colored areas on the map indicate where wells capable of furnishing 50 gallons per minute or more may be located. The techniques used to construct a well vary and depend on drilling depths and the geologic water-bearing formations below the surface. These supply water to the well. The United States Geological Survey offices in each state and other state water agencies can furnish information on groundwater availability and drilling depths. One type of irrigation well construction is called gravel-packed well. The gravel which surrounds the well casing prevents sand from entering the well. Farmers living in the eastern half of the United States under the riparian doctrine are entitled to reasonable use of water from a stream or lake. Those living in most of the western states must have earned the right by being the first to use the water under the prior appropriations doctrine. New water laws will no doubt be passed and existing laws revised as the competition for water increases. The distance between a water source and the field to be irrigated may be a deciding factor in determining whether or not to irrigate. There is no set rule on how far water can be pumped, but power or fuel costs, cost of pipelines, and associated costs should be carefully analyzed. The farmer may find the cost of drilling a well in the center of the field or constructing a reservoir or some other alternate source to be more economical than pumping from a distant source. In addition to the distance water must be pumped, the vertical height which water must be lifted or pumped determines pumping costs. The distance from water level to ground surface of deep wells should be added to the field elevation in determining total pumping lift or head. For surface water sources, the vertical distance from water level to the pump is also a part of the total pumping requirement. For centrifugal pumps, this distance should not exceed 15 feet. After determining the total water requirements of the crop to be irrigated and selecting a source of water, measuring the amount of water which can be pumped from the water source is often necessary. Approximate measurements may be made to determine the flow of water in a stream, the amount of water stored in a lake, pond, or reservoir, the flow or volume of water from a well, and the capacity of a combination of water sources. One method of determining flow in a stream is to multiply the average speed of flow in the stream by its cross-section area. The width of the stream times the average of several depth measurements across the stream gives you the stream's cross-section area. The average speed of stream flow can be estimated by marking off a known distance in the stream bed and recording the length of time needed for a floating cork to travel the distance. The product of cross-section area and speed of flow gives you the approximate volume of flow in cubic feet or meters per minute, which can be converted to liters or gallons per minute. Another method is the use of a weir notch, which is a more accurate measurement of stream flow. The quantity or volume of water flow is determined by first making measurements of depth of flow through the device and comparing these measurements to a table of values prepared for that service. A third method is the partial flume, which measures the depth of the water at 2 points in the flume by gauges. Then the quantity of water flow is determined from a table of values prepared for that particular flume. Your area engineer can help you with the procedures and tables for either of these methods. To estimate water stored in a lake, pond, or reservoir, first determine the surface area. The most convenient unit of measurement to work with is surface acres. Multiply the surface area by the average depth of the lake to find its volume. For a small lake, average depth is estimated as 4/10 of the greatest depth, usually at the dam. Good irrigation wells are the result of careful planning and depend largely on the skill and knowledge of a qualified well driller or contractor. There are two devices commonly used to determine flow from wells. One is a flow meter. There are several types of flow meters which can be installed in the delivery pipe near the pump discharge. They are usually calibrated to measure the amount of water that flows per minute. Another device is the orifice plate that is installed at the end of a level discharge pipe and will also give an accurate measurement of flow from deep wells. The height of the column of water in the glass tube is measured. This measurement is used with a chart of flow values for the size orifice used to determine the flow. Another important measurement to make while checking discharge from a deep well is drawdown. Drawdown refers to the distance that the water level drops from the time the pump is started until it stabilizes at a constant level. A simple method for measuring drawdown is with a weighted electrical contact lowered in the well. In certain situations, a combination of water sources may be needed to provide enough water to meet the irrigation requirements. Examples of this include a well pumping into a lake or pumping from a stream into a lake. Water from the well or stream may be supplied continuously to the lake during irrigation and between irrigation as required. After a plentiful water service has been determined, you should also determine if the water quality is satisfactory. Water quality can be affected by two conditions: chemicals contained in the water supply and the presence of trash, sand, and silt in the irrigation water. There is always a chance, although remote in most areas, of getting water from streams, lakes, ponds, or reservoirs, and sometimes from wells that contain chemicals that are harmful to plants. These chemicals are salts, chlorine, boron, industrial wastes, and organic acids and stains. If you suspect salts or other harmful chemicals in the irrigation water, the farmer should have both the soil and water tested by the State Soil and Water Testing Laboratory. Trash in the water is a problem with most irrigation systems using ponds, lakes, or streams as a water source. In addition, sand and silt in the water reduces the life of pumps and sprinklers. Special provision must be made for filtering or settling out trash and sand before they enter the irrigation system. You can see there are many factors that a farmer must consider in deciding whether or not to irrigate. In summary, the four factors which have a bearing on crop production as it relates to irrigation are the amount and timeliness of rainfall, the effect of supplemental water, the effect of land drainage, and the fringe benefits. The four most common sources of water are streams, lakes, ponds, or reservoirs, community pipelines or canals, and wells. Sometimes a combination of these sources may be used to provide the needed water. Stop the tape and complete Activity 1 for this module in the study guide. After completing this activity, change slide tray and tape to Part B of this module and start the presentation. This 5-part series is to introduce you to information necessary to help you assist farmers in planning a conservation irrigation system. Upon completion of this part of the module, you'll be able to discuss 4 basic methods of applying irrigation water and how you can help a farmer in selecting a method. When a farmer has decided to use irrigation, the next job is to decide which water application method to use. When selecting an irrigation method, several factors should be considered. What water application method to use, the effect of land slope, the effect of the soil's water intake, the effect of water holding capacity, the effect of water tolerance of crops, and the effect of wind action. There are 4 basic methods of applying water: the sprinkler method, the surface method, trickle irrigation, and below surface irrigation or sub-irrigation. With the sprinkler method, water is sprayed through the air and falls to the ground like rain. This is accomplished by using 1 or more rotating sprinklers or spray nozzles. With the surface method, water is applied at the ground level and flows by gravity over the surface of the field. This is accomplished in 2 ways. For close-growing crops, those sown, drilled, or sodded, the entire field is flooded. For row crops or crops in beds, the water is directed down furrows between the rows. The trickle irrigation method supplies filtered water directly onto or below the soil surface. Water is carried to each plant through an extensive pipe network. Water is then distributed around each plant into a wetted zone by a device called an emitter. Below surface irrigation is classified into 2 types: sub-irrigation and subsurface irrigation. With the sub-irrigation method, water is supplied to the root zone by artificially regulating the groundwater table elevation. In sub-irrigation, check dams and gates are used to maintain the water level in the soil from open ditches, or water is supplied through jointed or perforated pipe. In subsurface irrigation, water is applied below the surface through porous or perforated plastic pipe. Subsurface irrigation is similar to the trickle method, except in this case the water is applied directly into the root zone of the plant. The slope of the land may determine which water application method can be used. If the land is level, or can be made level without too much expense, the farmer can use any of the 4 methods of applying water. If the farmer has sloping land, irrigation may be limited to using the sprinkler or trickle method. In addition, you must know the water intake rate of the soil, how fast it can absorb water, to determine the maximum rate irrigation water can be applied. Irrigation water that is applied by a sprinkler faster than the soil can absorb it will result in surface puddling and erosion. Several conditions affect the intake rate of the soil. 2 important ones are the size of the soil particles and surface sealing, that is due to soil compaction and the presence of salts in the soil. Generally, the larger the soil particle size, the faster the water intake rate. Note how water intake decreases proportionately to the soil particle sizes. For example, if you have a very coarse textured soil, the intake rate may be as high as 100 millimeters per hour. Yet, a fine textured soil intake rate may be as little as 25 millimeters per hour. The water holding capacity of the soil must also be considered. The water holding capacity of soil is the amount of water it will hold after the free water has been drained away by gravity. Soil texture affects water holding capacity even more than it affects water intake rate. For example, note how water holding capacity decreases proportionately to the screen sizes of soil particles. If the soil is of a very coarse texture, The water holding capacity may be only 0.8 millimeters per centimeter of soil depth. Fine textured clay may hold as much as 2 millimeters per centimeter of soil depth. The water tolerance of the crops grown may be a factor affecting the selection of a water application method. For example, the sprinkler method, although adaptable to most crops, may help promote fungi and disease on the foliage and fruit of some crops. And the surface method, which is also adaptable to most crops, may be harmful to root crops and to plants that cannot tolerate water standing on the roots. Wind action also affects the water application method by distorting the water distribution pattern. Strong wind action may distort the water distribution pattern of the sprinkler method to the extent that you get little water on the windward side of the sprinkler and too much water on the other side. Often, high winds may affect the application efficiency of surface irrigation. This is particularly true on large, unplanted level areas. In summary, the four basic methods of applying irrigation water are the sprinkler method, the surface method, trickle irrigation, and below-surface irrigation or sub-irrigation. You have learned in this section how you can help the farmer select a compatible application method for their particular conditions. Stop the tape and complete Activity 2 for this module in the study guide. After completing the activity, change slide tray and tape to Part C of this module and start the presentation. This 5-part series is to introduce you to information necessary to help you assist farmers in planning a conservation irrigation system. Upon completion of this part of the module, you will be able to, 1, identify 3 main types of piping used for the mainline pipe unit. 2, identify 2 types of sprinklers most commonly used. And 3, identify the 3 basic sprinkler irrigation systems. After the farmer carefully considers the different methods of applying water, and if the farmer decides upon the sprinkler method of irrigation, the next step is to select a specific type of sprinkler system. No matter which sprinkler system you select, it will consist of 4 basic units. They are the pumping unit, the mainline pipe unit, the lateral pipe unit, and the sprinkler unit. The pumping unit takes water from the source and makes it available under pressure to the irrigation system. It may be driven by either an electric motor or by an internal combustion engine. Power units are generally equipped with safety shutdown controls that monitor the pumping unit. The safety shutdown controls for an internal combustion engine monitor the oil pressure, water pressure, and temperature of the power unit. The mainline pipe unit delivers the water from the pumping unit to the lateral or laterals. There are 3 main types of piping used for the mainline pipe unit. They are flexible and portable, rigid and portable, and permanent. The lateral pipe unit delivers the water from the mainline pipe unit to the sprinkler or sprinklers. The lateral pipe is of the same 3 general types as the mainline pipe, but usually is of smaller size. There are 2 types of sprinklers that are commonly used. They are the rotating or impact sprinkler and the spray-type nozzle sprinkler. To select a sprinkler system, you need to understand how the different systems work. For example, The fixed or sprinkler type system is so called because the basic units of the system are not movable. The solid set system is laid out to irrigate an entire area without being moved. It uses small to medium-sized sprinklers. The main line and lateral pipes are generally installed underground. Most permanent systems are designed to have only part of the sprinkler system operating at the same time. This is done by opening and closing control valves located at the sprinklers or on the lateral lines. The valves may be operated manually, or they may be remotely controlled from a centrally located control station or a substation. Automatic systems may be designed to start operating at certain time intervals. This type of system uses electric timers to start and stop each irrigation cycle. Automatic systems may also be activated by moisture sensing elements that are placed in the soil. The moisture sensing instruments start the system when water is needed and allow the system to operate until the entire field is irrigated. The water control valves of the multi-sprinkler permanent type irrigation system may be powered electrically, hydraulically using oil or water, or pneumatically using air. This remote controlled valve is powered by a combination of electric and hydraulic energy. The solid set portable system consists of enough laterals that have sprinklers to cover the entire field. This is how the name solid set came into use. With this type of system, the permanent main and lateral lines are generally laid out in the field immediately after planting and are not moved until the end of the irrigation season. When irrigating with the multi-sprinkler hand-moved semi-portable system, a part or all of the system may be operating at the same time, depending on the size of the system. The laterals are operated by the opening and closing of the hydrant valves, which are located either in the main line or at the sprinklers. The hand-moved lateral type of system was the first to make sprinkler irrigation popular. The periodic move, hand-moved lateral type consists of a main line and one or more laterals which are made of lightweight aluminum pipe with quick attaching couplings for easy movement by hand. The portable system is operated much like the semi-portable system, except that usually only one or two laterals are used at one time. The periodic move end-toe lateral systems are similar to hand-moved systems, except the laterals are mounted either on skids or wheels and moved with a tractor. Because of the towing, the pipe couplings for this type of system are stronger than the hand-moved pipe coupling. With some of the end-toe lateral systems, skid or wheel-mounted systems, capstan guides can be used to help guide and align the lateral as it is being moved to its new position on the opposite side of the main line. The periodic move, self-moved lateral type of irrigation systems are so called because they move from one set location to another under their own power. They are discussed as side wheel roll and side move types. The periodic move, side wheel roll type of system has a lateral made of either aluminum or galvanized steel pipe, which acts as an axle for wheels. The system uses small or medium-sized sprinklers mounted on the lateral, which may be as much as a half-mile long if you have smooth, level land. When irrigating, the lateral remains in one place until the amount of water needed has been applied. Then the lateral is moved by an air-cooled gasoline engine supplying power to the drive train. Most engines are located in the center of the lateral line. Self-aligning sprinklers are used on a side wheel roll lateral. As the lateral turns, the sprinkler support pipe rotates about the swivel joint, keeping the sprinkler upright. The periodic move, side move type of irrigation system is similar to the side wheel roll system, except that the lateral is mounted on towers. This type of system has two main advantages. The sprinklers remain upright at all times, and the lateral is high enough to move over tall crops such as corn. The continuous move laterals are self-propelled irrigation systems that represent a further development in sprinkler systems directed toward reducing the amount of labor required to operate a system. These systems are discussed as center pivot, linear move lateral traveling sprinkler. The center pivot type of system has a single lateral which rotates continuously about a center pivot. The lateral is usually made of painted or galvanized steel pipe connected by flexible couplings. It uses small or medium-sized sprinklers along the lateral and the larger nozzles at the outer end for equal distribution of water. The lateral is anchored at one end in the center of the field to a swivel joint that is called the center pivot. The lateral is supported by an under-truss system and towers that are made mobile by wheels. Water is supplied at the center pivot from a well located at the center of the field, or from a mainline supply. If the main line is above ground, provision must be made for each tower of the system to cross over the mainline pipe. When irrigating, the lateral rotates about the center pivot, wetting a circle from 100 to 500 acres. Note the green circular areas irrigated by a series of center pivot systems. Being self-propelled, the lateral is driven by a series of power units, one on each tower. The reason for the separate power units is to allow each tower to travel at a different rate of speed. The distance around the circle becomes greater as you move away from the center. Therefore, each succeeding tower must travel at a faster speed if the lateral is to rotate uniformly and in a straight line. Power to operate the lateral of a center pivot irrigation system may be either hydraulic, using water or oil, or electrical. Some water hydraulic drives operate with a water piston and a ratchet unit. The water pressure moves a piston which is connected to a ratchet drive. The ratchet drive pushes lugs on the wheels and thus causes the tower to move. Oil hydraulic drives use a hydraulic motor which is attached directly to the wheels. Power is usually supplied from an auxiliary hydraulic pump. The lateral is kept in alignment by a system of cables that extends the full length of the lateral. When one tower gets ahead or behind, a cable tightens. This opens or closes the proper valves to slow the drive mechanism or to speed it up, whichever is needed. Electrically driven center pivot irrigation systems have an electric motor on each tower. The electric motor drives each tower individually through a system of gears and chain or shaft drives. If one tower gets ahead of the others, an electrical switch is tripped which stops the motor. If the tower lags behind, another switch is tripped which restarts the motor. The speed of an electrically driven system is regulated by a control panel located at the pivot point. The use of non-rotating lower pressure spray nozzles is becoming increasingly popular with center pivot systems. Although these sprinklers reduce the energy requirements for pumping, they can have high application rates at the outer end of long lateral systems. Some are installed directly in the lateral, and others are installed on drop pipes. One of the principal objections to the center pivot system is that it covers only circular areas, leaving the corners of square fields unirrigated. This problem has been overcome, to varying degrees, by the use of large sprinklers at the outer end of the lateral, separate big gun corner systems, or special corner water systems. Large end sprinklers or volume guns are preset to operate when the lateral is traveling past the corner. In some low to medium pressure systems, a booster pump is automatically actuated to supply the required end gun pressure. Separate big gun corner systems may be one or more large volume guns which are moved or permanently located in the corners. Special corner watering systems are also attached to the outer end of the center pivot system. These systems include an auxiliary tower lateral system, electronically controlled by a buried guidance wire, and a pre-programmed telescoping end boom. Under some conditions where two fields do not need to be irrigated at the same time, a center pivot system can be used for both fields by moving the lateral from one field to another. Most systems are designed so that the wheels can be turned parallel to the pipe. Then the lateral can be towed with a tractor. The linear move type of system is designed to irrigate square or rectangular fields. It also moves continuously while sprinkling. The moving sprinkler lateral, the towers, and their drive mechanisms are similar to those used with a center pivot system. The part that is different is the self-contained power module that straddles the water supply ditch. The traveling sprinkler is a self-propelled type of system that moves continuously from one end of the field to another under its own power while sprinkling, using a big gun sprinkler to spray out the water. The cable tow traveler uses a flexible hose lateral which is dragged across the field by the same power that propels the sprinkler down the travel lane. The power is generated by a water-driven turbine. A steel cable anchored at the opposite end of the field guides the sprinkler as it moves. After the sprinkler reaches the opposite end, the hose is wound on the hose reel and moved to the next line. The cable is pulled out and re-anchored at the opposite end. The hose is unwound and reconnected to the main line. A new type of traveler irrigation system is the hose pull. This uses a large hose reel mounted on a four-wheel trailer. The reel is driven through a gearbox by a water turbine. During operation, the hose under pressure is continuously wound into the reel, pulling the sprinkler on a cart across the field. The hose reel and trailer are stationed at the main line, usually in the center of the field. The gun cart and hose are pulled back in. The machine is rotated to irrigate the opposite side of the field or move to the next travel lane. The slope of the land the farmer plans to irrigate can affect how satisfactorily the sprinkler system operates. Land that has a slope of less than 5% can use any type of sprinkler system you choose. Land that has slopes of approximately 5% or more may have problems with the multi-sprinkler, tractor move systems, and side wheel roll and side move systems. Self-propelled center pivot and lateral move systems may not maintain proper alignment on slopes of 20% or more. For land having slopes greater than 20%, irrigation may be limited to the use of hand move types, the single sprinkler self-propelled type, or the permanently installed type. Regardless of the type of systems used, erosion becomes more of a hazard on the steeper slopes. Rough land, such as that with irregular slopes, streams, and ditches, is a problem with most types of systems. Hand-moved and permanent systems can be designed to fit such conditions without too much difficulty. Self-propelled systems can be used on rolling land if a reasonably smooth path is available for the wheels to track, such as bridges over ditches and gullies, steps over piping and terraces, and flexible coupling in the lateral. The height of the crop the farmer plans to grow is a factor to carefully consider when choosing a sprinkler irrigation system. In summary, The three main types of piping used for the mainline pipe unit that delivers water from the pumping unit to the lateral or laterals are flexible and portable, rigid and portable, and permanent. The two types of sprinklers most commonly used are the rotating or impact sprinkler and the spray-type nozzle sprinkler. The three basic sprinkler irrigation systems are multi-sprinkler, single sprinkler, and boom sprinkler. Stop the tape and complete Activity 3 for this module in the study guide. After completing this activity, change slide tray and tape to Part D of this module and start the presentation. This 5-part series is to introduce you to information necessary to help you assist farmers in planning a conservation irrigation system. Upon completion of this part of the module, you'll be able to, 1, name the 5 basic units in a field-sized surface system. 2, name the 5 different types of graded surface irrigation systems. If the farmer has decided that the surface method of irrigating is needed, the next step is to select a specific type of surface system. As with the sprinkler method, you will first need to understand the differences in the various surface irrigation systems. There are normally 5 basic units to a field-sized surface system that are common to all types. They are a source of water, a field supply line, a measuring device, a head ditch or pipe, and turnouts and checks. In addition, provisions for holding the water within a certain area are necessary for collecting excess water into a tail ditch or a reservoir for reuse. For surface irrigation, the entire surface is flooded, or water is applied to furrows. Sources of water for surface irrigation are surface water or groundwater. Water travels to the field through open ditches or through pipelines. Water from the supply lines flows into a head ditch or a pipeline that extends along one end or one side of the field to be irrigated. Turnouts are used for releasing the water from the head ditch or pipeline into the land to be irrigated. Turnouts may be floodgates, or siphon tubes. With a pipeline system, use gated pipe. Or a hydrant valve. With an automated surface system, use the type of checks and turnouts that are adaptable to the automatic controls. Provisions for holding the water in the area to be irrigated are necessary to most surface systems. They're called levees, dikes, or borders. Each is essentially the same. They consist of a ridge of earth formed from the field soil to enclose the area to be irrigated. The term levee will be used in this presentation. A reuse reservoir or tailwater ditch collects excess water for reuse. This arrangement allows for higher flow rates, which increases the uniformity of water application, saves the excess water for reuse, and prevents fertilizers, pesticides, and salts from entering and polluting streams. Surface systems are designed for both level land and sloping land areas. For the purpose of this discussion, systems that are designed for level land are called level systems, and systems designed for sloping land are called graded systems. The level border type of surface system consists of a level area enclosed by earthen border ridges or levees. When irrigating, a predetermined amount of water is turned on the strip and allowed to stand until it is absorbed. For a uniform distribution of water, the rate at which the water is turned onto each strip should be at least twice as fast as the soil can absorb it. The contour levee type of surface system is similar to the level border system, except it is adapted to slightly sloping land. With this type of system, the levees are graded to contour with the shape of the field. When irrigating, the procedure is the same as the level border type of surface system. Contour levees are also used in rice production, where the entire field is kept flooded for most of the cropping season. The level furrow type of surface system is the same as the level border type, except for the addition of furrows. When irrigating, a stream as large as the furrow will carry without causing erosion is turned into each furrow by siphon tubes or gated pipe. The water is allowed to stand in the furrows until it has been absorbed into the root zone below the furrows and in the ridges between the furrows. There are 5 types of graded systems. They are graded border, contour ditch, graded furrow, corrugation, and contour furrow. Graded systems are usually used on gentle slopes, although contour ditch systems are used on steeper slopes, on sod pasture, or hayland. When irrigating, water is turned in at the upper end of the strip and flows down the slope until the entire area is wet to the desired depth. The graded border type of surface irrigation is the same as the level border type, except that it has some slope in the direction of the water flow. Graded borders can be laid out on a contour on sloping fields by bench leveling. A slight grade is established in the direction of the contour. The contour ditch type of surface system is laid out on sloping land after the crop is planted. When irrigating, a temporary dam is made in the head ditch just below the contour ditch. The water in the contour ditch is also checked by a temporary dam. Water then flows around the slope in the contour ditch on the upper side of the strip to be irrigated. And as the water rises in the contour ditch, it floods over into the strip below. The graded furrow type of surface system consists of channels between rows or beds. The slope should be uniform in the direction of the water flow. When irrigating, the water is turned into the graded furrows at the upper end through siphon tubes or gated pipes. It flows to the other end, being absorbed into the soil as it goes. In furrow irrigation, a large, non-erosive furrow stream is necessary to advance the water rapidly from the head to the tail of the field to get uniform application of irrigation water down the length of the field and minimize deep percolation losses. After the water has advanced to the tail, the large stream size will be more than is needed to provide the infiltration to the root zone and excess runoff results. If a small furrow stream is used, the advance will be slower, resulting in more deep percolation toward the upper end, but the runoff will be less. If a large initial stream size is used to advance the water down the furrow, and a smaller cutback furrow stream is used to provide the in-soak, both deep percolation and runoff will be minimized. Cutback irrigation isn't popular because of the labor requirement and other management problems. 2 recent innovations are becoming popular in furrow irrigation. These are known as cablegation and surge irrigation. They have similar results as cutback irrigation and do it automatically. In cablegation, a pipe with openings for each furrow is installed across the top of the field on a slope with the openings near the top of the pipe. A traveling plug in the pipe is attached by a cable to a reel with speed control. As the water pushes the plug down the pipe, water flows out of the opening upstream from the plug and down the furrows. Because of the slope in the pipe, the opening nearest the plug has maximum flow, and the flow decreases to zero flow upstream from the plug. This provides a large initial stream size for advance and smaller stream size for in-soak period. Surge irrigation alternates the irrigation water between two sets of furrows on a set cycle time. The switch is accomplished with a surge valve and an automatic controller. For example, the irrigator might run water down the right set of furrows for 90 minutes from 6 to 7:30, and then the left set from 7:30 to 9 for the first cycle. The controller will switch the water back to the right set from 9 to 10:30, and then to the left set from 10:30 to 12 to complete the second cycle. And so on for each cycle until the irrigation is complete. General experience has been that the same stream size will advance down both sets of furrows using surge in nearly the same amount of time it takes the conventional method on one set of furrows, or advance down twice as many furrows with the same amount of water. The result is less deep percolation toward the upper end of the field. The reason for the surge effect is not fully understood, except experience shows that each time water is returned to the furrow, it flows rapidly down the previous wetted furrow at a much faster rate. The corrugation type of surface irrigation is a small graded furrow method for sown or sodded fields. When irrigating, water is turned into the small channels that are evenly spaced across the field. The water soaks into the soil and spreads laterally to irrigate the entire area. The channels are spaced so that the water wets the soil in the ridges by the time it has finished flowing in the furrows. The contour furrow type of surface system is similar to the graded furrow system, except the furrows are laid out across the slope on a uniform grade. The size and spacing of the furrow depend on the crops grown and the equipment used. The furrow systems can be used on nearly all cultivated crops grown in rows. The slope of your field is critical when selecting a surface irrigation system. If the farmer's field slopes are practically level, less than 0.1%, use one of the level types of systems that has a minimum of land preparation. If the field has more than 0.1% slope, use one of the graded types of systems. A competent person must lay out whatever type of surface system selected if it is to provide satisfactory irrigation service to meet the needs. If the farmer has soils that have a slow to moderate intake rate, any type of surface system may be used. An exception is a soil that has a very low intake rate. With fine textured soil, use one of the furrow systems. If the soil has an extremely high intake rate, the use of a surface system may not be possible. The intake rate may be so high that the farmer will not be able to get water to flow a reasonable distance before it has been completely absorbed. The level border and contour levee systems are more easily adapted to irregularly shaped fields. The amount of water needed for the entire field can best be determined by your design engineer. There are two special soil conditions that will affect the selection of a surface system. They are soil that has a tendency to bake and crack, and soil that has a high salt content. If the soil is fine textured and tends to bake and crack, use the level furrow or level border system. If the soil has a high salt content that needs to be leached away, the level border and contour levee systems are most effective. The crops grown and cultivating practices used will help determine the type of surface system to use. The factors you have learned from this section will help you decide which system to use for the surface method. In summary, there are normally 5 basic units in a field-sized surface system that are common to all types. They are a source of water, a field supply line, a measuring device, a head ditch or pipe, and turnouts and checks. The 5 different types of graded surface irrigation systems are graded border, contour ditch, graded furrow, corrugation, and contour furrow. Stop the tape and complete Activity 4 for this module in the study guide. After completing the activity, change the slide tray and tape to Part E of this module and start the presentation. This 5-part series is to introduce you to information necessary to help you assist farmers in planning a conservation irrigation system. Upon completion of this part of the module, you'll be able to, 1, name the 5 basic units of a trickle irrigation system, and 2, name the 4 types of trickle irrigation. There are 2 more types of irrigation systems to consider. They are trickle and sub-irrigation. If the farmer decides that the trickle method of irrigating is best suited to the farm operation, the next step is to select a specific type of trickle system. This section explains how each type works and what criteria must be considered in making the proper selection. All trickle irrigation systems are comprised of 5 basic units. They are the pumping unit, the control head, the main and sub-main lines, the laterals, and the emitters. The pumping unit takes water from its source and makes it available under pressure at the control head. It is driven either by an electric motor or by an internal combustion engine. The power units are generally equipped with safety shutdown controls in case of a loss of water pressure, excessive temperature, or a loss of oil pressure. The control head serves as a control station for the trickle irrigation system. The control head generally consists of the water measuring device, valves, injectors, automatic controllers, pressure regulators, and filters. In some installations, additional pressure regulators and filters are located at the entrance to the manifold or lateral lines. The main and sub-main lines are the water delivery pipelines that supply water to the lateral lines from the control head. These lines are usually installed below the ground surface. The main and sub-main lines may be constructed of polyethylene, rigid PVC, galvanized steel, or asbestos cement. Whatever the material used, it should be non-corroding and non-sealing to prevent contamination problems from within the pipe system. The lateral lines supply water to the emitters from the main, sub-main, or manifold lines. Pressure in the laterals is low, generally in the range of 5 to 25 pounds per square inch. Emitters are the devices used to control the discharge from the lateral lines. Point source emitters discharge water from the points that are individually and relatively widely spaced, usually over 1 yard. Multiple outlet emitters provide water at 2 or more emission points. Line source emitters discharge water from closely spaced perforations or a porous wall along the lateral line. There are 4 types of trickle irrigation systems. The primary difference between these types is the design of the emitter that is used to apply water to the plants. The 4 types of systems are usually classified as the drip system, the subsurface system, the bubbler system, and the spray system. The drip system slowly applies water to the soil surface as small or continuous drops through emitters. Emitters can be single outlet, multiple outlet, or line source type. During irrigation, the emitter drips or oozes water at a constant, low discharge rate, normally a few liters per hour. The type and arrangement of the emitters depend on the crop being irrigated. The subsurface system is identical to the drip system in all but one respect. The laterals and line source emitters are located below the soil surface. The bubbler type system applies water to the soil surface as a small stream or fountain. Discharge rates are greater than for the drip or subsurface systems, but generally less than 1 gallon per minute. Spray systems apply water by a small spray or mist to the soil surface. Consequently, the air distributes the water rather than the soil, as is the case with the other three systems. Discharge rates for spray-type emitters are generally less than a half gallon per minute. Trickle irrigation requires water free of foreign matters. Clogging of emitters is the most difficult problem encountered in trickle irrigation systems. The nature or characterization of the particulate matter that may clog the emitter depends to a large extent on the source of water. All water entering the system requires filtration. The extent of filtration depends upon the type of emitters used and the amount and characteristics of the contaminants present in the water. Several types of filters are used with trickle irrigation systems, such as the screen type and the graded sand type filter. In addition, settling ponds are used to remove heavy loads of sand. Again, the type of filter necessary depends on the trickle system selected and the particulate matter in the water supply. This determination can best be made by professionals who specialize in irrigation systems. Like other irrigation systems, the slope of land should be carefully considered when choosing a trickle system. If the farmer has land that has slopes of less than 5%, any type of trickle irrigation system could be used. If the land has slopes of 5% or more, the subsurface and bubbler systems generally will not be suitable. However, the drip and spray systems can be adapted to any farmable slope. The rate of water absorption of the soil will determine the number, discharge rate, and spacing of the emitter and, to some degree, the type of system to select. If the soil absorbs water slowly, select emitters with low application rates. However, the low absorption rates are generally associated with fine textured soil. In this soil, water will move farther from emitters, thus a smaller number of emitters are required per plant. Just the opposite is true with most coarse textured soil. Thus, in coarse textured soil, use a larger number of emitters per plant to meet the water needs of the crop. The trickle irrigation system is adaptable to most orchard, vineyard, and row crops. But each type of emitter should be carefully examined for each particular crop. The trickle irrigation system is not well suited to use with crops that have been sown, drilled, or sodded. The non-uniform water application and the high cost of the trickle systems have resulted in their limited use with these types of crops. If the farmer has decided to use the sub-irrigation method of irrigation, the choice of a system will be relatively easy. There are only two commonly used types of systems from which to choose: open ditch and underground conduit. You must remember, however, that sub-irrigation is confined to certain conditions. You must have a natural high water table or impervious layer below the root zone from which an artificial water table can be maintained. Also, the water table and field surface must be level. Sub-irrigation systems are somewhat similar to surface systems. The basic units of a sub-irrigation system consist of a source of water, a combination field supply line and disposal ditch, head ditch or head pipeline, open ditch laterals or pipeline laterals, check dams, and dispersal ditches if not combined with the field supply line. Basically, there are two types of sub-irrigation systems: the open ditch type and the underground conduit system. When irrigating, the operation of both the open ditch and underground types is the same. As the name implies, sub-irrigation systems distribute the water below the ground level. Because the water is applied below the surface, the water moves by capillary action to the root zone of the plant. Sub-irrigation may be used for field crops and pasture, as well as orchards and vineyards. The permeability or water intake rate of the soil is a main factor to consider in selecting a subsurface system. Another factor that the farmer should consider when selecting the system is the amount of energy required to operate an irrigation system. Surface irrigation requires no pumping energy to apply irrigation water. Trickle irrigation requires a moderate level, and sprinkler systems require a high level of energy input to operate the systems. Water management through irrigation may become a profitable production practice. In summary, the 5 basic units of a trickle irrigation system are the pumping unit, the control head, the main and sub-main lines, the laterals, and emitters. There are 4 types of trickle irrigation systems. The primary difference between these types is the design of the emitter that is used to apply water to the plants. The 4 types of systems are usually classified as the drip system, the subsurface system, the bubbler system, and the spray system. In this 5-part series, you have learned there are 4 factors to be considered, all of which have a bearing on crop production as it relates to irrigation. They are the amount and timeliness of rainfall, the effect of adding supplemental water by means of irrigation, the effect of land drainage, and the fringe benefits attributable to irrigation, which are sometimes as important as the water itself. There are 4 basic methods of applying water: the sprinkler method, the surface method, trickle irrigation, and below-surface irrigation or sub-irrigation. When selecting an irrigation method, there are several factors which should be considered. They are what water application method to use, the effect of land slope, the effect of the soil's water intake, the effect of water holding capacity, the effect of water tolerance of crops, and the effect of wind action. The Soil Conservation Service assists farmers in planning a conservation irrigation system that is adapted to the soil, the topography of the land, the energy in dollars, and the crops raised. The system will efficiently use the water resources and will minimize erosion. Stop the tape and complete Activity 5 in the study guide. After completing this activity, ask your trainer for the test for this module.